Thanks to Squarespace for sponsoring this video. Have you ever wondered how black holes challenge our understanding of the universe? Today, we're diving deep into some of the most profound questions about black holes. Did a black hole create our universe? How could black holes potentially delete the universe? Do black holes prove we live in a holographic universe? Is the inside of a black hole secretly on the outside? How do black holes form? Is a black hole a 2D or a 3D object? What shape are black holes? What happens at a black hole's event horizon? How does space-time change inside a black hole? How black holes become supermassive? How does gravity escape a black hole? What happens at the center of a black hole? What is on the other side of a black hole? Can black holes transport you to other worlds? Has anyone created a black hole on Earth? Can black holes cause dark energy? Do black holes live forever? Let's delve into the answers to these questions with a comprehensive scientific perspective. The 20th century witnessed transformative breakthroughs in our cosmic understanding, blending new discoveries with changing perspectives. Initially, the Milky Way was presumed to be the cosmic boundary, housing all known celestial entities. This view was complemented by the idea of a constant universe, timeless in its existence, and seemingly operating under the immutable laws of Newtonian physics. Yet as the century progressed, this notion was upended by the advent of quantum mechanics and the theory of relativity, introducing concepts of a dynamic, evolving universe, far beyond the simplistic, eternal cosmos once imagined. This perspective underwent a radical shift within just a few years. Einstein's theory of general relativity overtook Newton's gravitational laws, revealing the intricate relationship between matter-energy and the fabric of space-time. His equations suggested a universe in constant flux, not static, a concept later confirmed by the discovery of an expanding universe. His theory even predicted black holes, which were subsequently discovered and directly imaged. This led to an exciting and speculative idea. The universe might have originated from a black hole. The crux of this idea lies in the nature of a black hole's event horizon. This boundary creates different realities for objects inside and outside of it. An object outside a black hole's event horizon can feel its gravitational pull due to the warping of space, but can still escape its grasp. In contrast, once an object crosses into the event horizon, it's inevitably drawn towards the black hole's singularity, adding to the black hole's mass. But what does this have to do with our universe? By adding up all the known forms of matter and radiation in the observable universe, which includes regular matter, neutrinos, dark matter, photons, and gravitational waves, we can calculate an equivalent mass for the universe using Einstein's equation E equals mc squared. This approach leads us to a remarkable insight. If the entire universe were compressed into a single point, it might form a black hole. This hypothesis, while still speculative, offers a fascinating perspective on the origins and nature of our universe. Let's ponder a profound question. What would happen if the entire universe were compressed into a single point? According to Einstein's gravitational theory, such a scenario would result in the formation of a black hole. Interestingly, the size of this hypothetical black hole, determined by what's known as the Schwarzschild radius, depends solely on the mass involved, provided the mass energy isn't charged or spinning. Here's where it gets fascinating. The Schwarzschild radius of a black hole containing all the matter in the observable universe almost exactly equals the size of the universe we can see. This striking similarity raises an intriguing possibility. Could our universe be, in some way, inside a black hole? This concept becomes even more captivating when we consider a discovery from the 1960s, the cosmic microwave background. This is a uniform, low-energy radiation that permeates the entire sky, maintaining a consistent temperature of about 2.725 Kelvin, just above absolute zero. Its uniformity and perfect blackbody spectrum suggest a hot, dense past for our universe. This idea aligns with the Big Bang theory, where the early universe resembles a singularity, a state also found at the cores of black holes, where conventional physics ceases to apply. Delving into the equations that describe black holes adds another layer to this mystery. If you start just outside a black hole's event horizon and measure your distance as you move away, that distance stretches from the Schwarzschild radius to infinity. However, if you start just inside the event horizon and measure your distance to the singularity, that distance compresses from the Schwarzschild radius to zero. This contrast in behaviors is not only fascinating, but also deepens our curiosity about the relationship between black holes and the universe. It's more than just a big deal, it's a profound revelation. When you closely examine the properties of space outside and inside a black hole's event horizon, from its Schwarzschild radius, r, to infinity and from r to 0, respectively, you find a stunning similarity. They are mathematically identical at every point. This surprising result emerges simply by flipping the distance variable, r, to its inverse, 1 over r. This discovery suggests an almost mirror-like equivalence between the black hole's interior and its exterior. Our understanding of the universe has been revolutionized by two major discoveries in recent decades. First is cosmic inflation, which suggests that the universe didn't start from a singular point, but from a rapid, exponential expansion phase before the hot Big Bang. This implies the existence of an energy field intrinsic to space itself, driving the universe's inflation until it gave way to the hot Big Bang. The second groundbreaking discovery is dark energy. As the universe expands and thins out, distant galaxies are seen to move away faster, indicating an energy inherent to space that doesn't diminish with expansion. This has led to intriguing speculations. Could there be a link between the mechanisms of black holes and these cosmic phenomena? Black holes grow by accumulating matter and shrink by emitting Hawking radiation. Is it possible that changes in the black hole's event horizon influence the energy within spacetime? Could cosmic inflation be a result of our universe emerging from a massive black hole? Might there be a connection between dark energy and black holes? This line of thinking extends to an even more captivating concept, the idea that black holes within our universe might be birthing new, baby universes. While these theories have been around for a long time, they remain unproven. Several models and ideas exist, fueling the curiosity of those studying black holes, thermodynamics, entropy, general relativity, and the cosmic life cycle. However, every model proposed so far hasn't quite hit the mark in replicating the successes of the inflationary hot Big Bang model, explaining unaccounted phenomena or making testable new predictions. A notable attempt in this regard is Roger Penrose's conformal cyclic cosmology, which predicts the existence of Hawking points in the cosmic microwave background. Sadly, these features haven't been consistently observed, leaving the theory speculative. The idea of a connection between black holes and the birth of universes is fascinating from both physical and mathematical perspectives. It's plausible that our universe could have originated from an enormous black hole in a previous universe, and that every black hole in our universe might be creating new universes within. However, the missing piece is a unique, identifiable signature that could confirm these theories. This remains a significant challenge for theoretical physicists, who strive to distinguish new ideas from established ones. Until this breakthrough occurs, these theories will remain intriguing, yet unconfirmed possibilities. The notion that our universe might have been born from a black hole is tantalizing, and it's too early to discount it completely. Thanks to Squarespace for sponsoring this video. Squarespace is an all-in-one website platform to build a strong online presence and run your business. With Squarespace, creating a stunning website is a breeze, no matter your skill level. Their award-winning templates are not just visually appealing, but also incredibly user-friendly. Whether you're an artist, entrepreneur, or hobbyist, you can easily build your own website without needing to know any coding or hiring a professional designer. Plus, if you ever get stuck, you can always reach their 24/7 customer support to guide you through. Simplifying every aspect of your business from website creation and online stores to marketing tools and analytics, Squarespace is the perfect tool to start your online journey. Go to squarespace.com/bigscientificquestions and use the promo code BIGScientificQuestions to save 10% off your first purchase of a website or a domain. Black holes, the most formidable and mysterious entities in the universe, possess an extraordinary power that is both fascinating and intimidating. They are capable of disintegrating entire stars, breaking them down into particles as small as atoms. This process can be likened to an incredibly powerful cosmic blender, capable of reducing solid, massive celestial bodies into their most fundamental components. Beyond this remarkable ability, black holes also hold the ominous potential to obliterate the universe itself, a concept that stirs both awe and existential dread. The formation of black holes is a process where an immense amount of matter is compressed into an extraordinarily small space. Imagine taking the mass of an entire mountain range and compressing it into a space as small as a pea. This results in an object of extraordinary density and gravitational pull. At the core of a black hole, this gravitational force is so intense that it tears apart anything that ventures too close, much like a powerful whirlpool in the ocean that can drag down ships and anything else caught in its grasp. These cosmic phenomena are so dense that they create a point of no return known as the event horizon. Not even light, the fastest thing in the universe, can escape from within this boundary, rendering black holes as dark, empty voids in space. Approaching a black hole is akin to drifting towards a colossal waterfall in a river. Initially, the journey might seem tranquil, but as one nears the event horizon, the gravitational pull becomes irresistible. This is similar to being caught in a strong river current that inevitably leads to a waterfall. Once you reach a certain point, there's no turning back, and you're swept over the edge into the unknown. One of the most intriguing aspects of black holes is their process of mass loss, known as Hawking radiation. This phenomenon is akin to a leaky faucet that loses water at an imperceptibly slow rate. For a black hole with a mass comparable to our Sun, it would take a time span so vast to lose just a tiny fraction of its mass. This gradual process leads to the eventual shrinking and disappearance of black holes, occurring long after the last stars in the universe have extinguished, leaving behind only a faint trace of radiation. The mystery of black holes deepens when considering their interaction with information. In physics, information refers to the specific arrangement of particles that gives everything in the universe its identity. It's like having different recipes that can turn the same ingredients into either a cake or a loaf of bread. This information, according to our current understanding of physics, cannot be destroyed, only transformed. If you burn a book, for instance, the book turns to ash. But in theory, if you could capture and analyze every particle of smoke and ash, you could reconstruct the information that was in the book. The information isn't lost, it's just transformed into a different form. If we could measure every particle, atom, and wave of radiation in the universe, we could, in theory, trace back all information to the very beginning of the universe. However, black holes challenge this concept by seemingly erasing information, much like a paper shredder that destroys documents beyond recognition. To address this conundrum, several theories have been proposed. One theory posits that when black holes vanish, they take all the trapped information with them, similar to a locked safe filled with secrets being thrown into the depths of the ocean, never to be found or opened again. Another theory suggests that black holes might conceal the information in a place beyond our reach, akin to a magician's trick where an object disappears and reappears in an unexpected location, leaving the audience baffled. Yet another hypothesis proposes that black holes store information on their surface. This can be visualized by imagining a balloon with a picture painted on it. As the balloon inflates, the picture stretches, but remains visible. Black holes might operate in a similar manner, storing and expanding information on their surface. This leads to the revolutionary concept of the holographic principle, which suggests that our entire universe might operate in a similar fashion. It's as if we are living in a 3D movie that's actually being projected from a flat screen. Everything we perceive in 3 dimensions might actually be encoded on a 2-dimensional surface. This is like an artist creating a mural that appears 3-dimensional from a distance, but is actually painted on a flat wall. This theory, complex and deeply rooted in advanced physics, string theory, and mathematics, offers a radical new perspective on the universe. It implies that black holes could be the key to unlocking the true nature of reality, much like discovering a hidden layer in a painting that changes our entire perception of the artwork. In summary, black holes are not just fascinating celestial objects, but are also at the forefront of challenging and expanding our understanding of the universe. Their ability to warp space and time, their slow process of mass loss, and their potential role in the preservation or destruction of information make them a central focus in modern astrophysics. As we continue to study these cosmic giants, we may find more clues that could lead to a deeper understanding of the universe and our place within it, much like piecing together a cosmic puzzle that spans the entirety of space and time. The study of black holes is not just about understanding these mysterious objects themselves, but also about unraveling the fundamental laws that govern our universe. It's a journey that takes us to the very edges of science and philosophy, challenging our perceptions of reality and our place in the cosmos. As we delve deeper into the mysteries of black holes, we may find answers to some of the most profound questions about the nature of existence and the ultimate fate of the universe. For the past 100 years, the greatest scientific debate has been a clash between Albert Einstein's own theories. On one hand, there's the Einstein who, in 1915, developed the theory of general relativity. This theory portrays gravity as the distortion of spacetime by matter and energy. It suggests that spacetime can bend, expand, tear, vibrate like a bowl of jello, and vanish into the enigmatic voids known as black holes. On the other hand, there's the Einstein who, beginning in 1905, established the basis for quantum mechanics. These unconventional rules introduce randomness into the universe, a concept Einstein never fully embraced. Quantum mechanics proposes that a subatomic particle, like an electron, can exist simultaneously in multiple places, and a cat can be both alive and dead until it's observed. Einstein often protested, saying God doesn't play dice with the universe. Gravity dominates outer space, molding galaxies and the entire universe, while quantum mechanics governs the microcosm of atoms and fundamental particles. These two domains seemed entirely separate, leaving scientists puzzled about phenomena in extreme conditions like black holes or the universe's inception. However, recent intense research into the inner workings of black holes has unveiled surprising links between these two cosmic perspectives. The ramifications are astonishing, including the notion that our three-dimensional universe, and even ourselves, might be holographic, resembling the ghostly security images on some credit cards and driver's licenses. In this cosmos model, there is no distinction between here and there, cause and effect, inside and outside, or even past and present. Household cats could materialize from thin air. We might all become akin to Dr. Strange. Leonard Susskind from Stanford University suggested in a 2017 paper that while it might be an overstatement to claim gravity and quantum mechanics are the same, there is a growing perception among experts that the two are inextricably linked, with each requiring the other to be fully understood. This perspective, as advocated by Dr. Susskind and his team, holds potential for developing a unified theory that merges gravity and quantum mechanics, known as quantum gravity. Such a theory could potentially offer insights into the origins of the universe. In 1935, Einstein was involved in publishing two notable papers that highlighted a contrast in his theoretical perspectives. The first paper, co-authored with Nathan Rosen, suggested, according to general relativity, that what are now known as black holes could exist in pairs, linked by passages through spacetime named Einstein-Rosen bridges, or wormholes. This concept sparked interest in the realm of science fiction, suggesting the possibility of travel between these black holes. The second paper, co-written with Rosen and Boris Podolsky, aimed to critique quantum mechanics by pointing out what they perceived as a logical inconsistency. They noted that, as per quantum mechanics, once connected particles would remain interconnected, regardless of the distance separating them. The act of measuring one particle's attribute would immediately influence its counterpart. This idea, which Einstein referred to as spooky action at a distance, is now understood as entanglement, and has been substantiated through various laboratory experiments. Recently, the Nobel Prize in Physics was awarded to physicists who provided experimental confirmation of this phenomenon. The concept of quantum entanglement has been described by physicist N. David Mermin as resembling a form of magic, given its unusual nature. Daniel Kabat has further explained this phenomenon by stating that, contrary to common belief, information about an object is not just confined to the object itself. Entanglement implies that objects do not possess an independent existence with definitive properties, but are defined through their relationship with other objects. It is unlikely that Einstein saw a direct connection between these two papers in 1935. Modern physicists, however, are exploring the idea that wormholes and entanglement may be related aspects of a larger, more complex theory, potentially offering solutions to various cosmic enigmas. In the eyes of astronomers, black holes are enigmatic entities with such intense gravity that they can engulf stars, disrupt galaxies, and capture light. At a black hole's boundary, time appears to halt, and at its core, matter is compressed to infinite density, causing conventional physics to collapse. However, for physicists delving into fundamental laws, black holes are a treasure trove of mysteries and imaginative possibilities. In a groundbreaking revelation in 1974, cosmologist Stephen Hawking demonstrated that black holes are not completely black or permanent, especially when quantum effects are considered. He suggested that over vast periods, a black hole could emit energy and particles, diminish in size, heat up, and eventually explode. This process would release all the mass that had been absorbed into the black hole, dispersing it back into the universe as a chaotic burst of particles and radiation. This concept might seem like a form of cosmic rebirth, but it posed a significant challenge to a fundamental scientific principle: the conservation of information. According to this principle, it's theoretically possible to trace or predict the trajectory of objects, like billiard balls on a pool table, even if they fall into a black hole. However, if Hawking's theory was accurate, the emissions from a black hole would be random, a thermal noise devoid of any details of the objects consumed. For instance, if a cat were to fall into a black hole, most of its information, such as its name, color, and nature, would be irretrievably lost, akin to finding personal documents missing from a safe deposit box. Hawking suggested in 1976 that this randomness was akin to God playing dice in an unseen manner. This assertion sparked decades of intellectual debate. Dr. Susskind, who emerged as a prominent opponent to Hawking's theory, initially struggled to reconcile with Hawking's proposition, finding it counterintuitive. The concept of reality being encoded like a hologram emerged to Dr. Susskind in 1993 during a stroll through a physics building on his campus. He came across a holographic display of a young woman, sparking an insight. A hologram is essentially a three-dimensional image, such as a teapot, a cat, or a character from a film, produced entirely from light. It's crafted by shining a laser on the actual object and recording the light's reflection patterns on a photographic plate. When this plate is later illuminated, a three-dimensional image of the object appears. Dr. Susskind found himself contemplating this scenario where information seems to exist in two different forms: the visible, seemingly real object, and the information encoded on the film of the hologram, which, when examined closely, appears as a collection of intricate patterns. He realized that the right pattern on the film could bring any image into 3 dimensions. This led him to ponder: what if a black hole was akin to a hologram, with its event horizon acting as the film, encoding the contents within? He recalled this as an unconventional yet intriguing idea. Meanwhile, Dutch physicist and Nobel laureate Gerardus 't Hooft at Utrecht University was contemplating a similar notion. Under Einstein's general relativity, he considered that the information content of any 3-dimensional space, like a living room or the entire universe, is confined to the amount of data that can be encoded on a hypothetical surrounding surface. This encoding happens at an incredibly fine scale, measured in pixels about 10 to the negative 33rd centimeters across, known as the Planck length. With such minuscule data pixels, the information capacity would be extraordinarily high, yet finite. According to a limit established by Jacob Bekenstein, then a Princeton graduate student and a rival of Hawking, overloading a region with too much information would lead to the formation of a black hole. Dr. 't Hooft summarized this discovery about the universe's method of data management in 1993. Nature's record-keeping system allows data to be inscribed on a surface, and the tool for writing this data has a finite size. The concept of the universe as a holographic projection reached its most comprehensive form in 1997. Juan Maldacena, a theoretical physicist at the Institute for Advanced Study in Princeton, New Jersey, utilized emerging ideas from string theory, a hypothetical theory of everything that depicts subatomic particles as vibrational strings, to mathematically model the universe as a hologram. In Maldacena's model, all information occurring within a specific space volume is encoded as quantum fields on the surface of that space's boundary. This model of the universe has been likened to a soup can. The contents of the universe, including galaxies, black holes, gravity, stars, and everything else, represent the soup within the can, while the information describing these contents exists on the exterior, similar to a label. This analogy creates a visual of gravity encapsulated within a can, where the interior and the exterior, or the bulk and the boundary, are different but complementary ways of describing the same phenomena. As the fields on the can's surface follow quantum principles that ensure the preservation of information, the gravitational fields within must also maintain information integrity. In this framework, Maldacena stated in a 2004 conference that there is no possibility for information loss. Hawking eventually acknowledged this perspective, indicating that gravity does not lead to the loss of information after all. Dr. Susskind, commenting on this holographic universe concept, noted in an interview that this implies the universe is coherent and makes sense. He described the idea as extraordinary, suggesting a hypothetical scenario where a large, hollow sphere made of silicon and other materials, inscribed with specific quantum fields, could be used in advanced laboratory experiments. Interacting with this sphere could potentially yield responses from the hypothetical entities within it. Yet, if one were to open this sphere, it would appear empty. This leads to the intriguing conclusion that we, as inhabitants of the universe, do not merely observe the hologram, we are part of the hologram itself. In the real universe, unlike Dr. Maldaceno's mathematical model, there is no discernible boundary or outer limit. Yet for physicists, his model has been a validation that gravity and quantum mechanics can coexist harmoniously, providing insights into the workings of our actual universe. Dr. Maldaceno has acknowledged that his model doesn't directly address how information escapes black holes intact, or where Hawking's 1974 calculations might have erred. During the 1990s, Don Page, a former student of Hawking at the University of Alberta, proposed an alternative theory. He suggested that if a black hole preserves information while evaporating, then its particle emissions are not as random as initially thought by Hawking. Over extended periods, emitted particles would increasingly correlate with previously emitted ones, gradually revealing the concealed information. After an immensely long time, all hidden information would be released. This theory required that particles currently escaping a black hole be entangled with those emitted earlier. However, this raised a quantum quandary. The newly emitted particles were also entangled with their counterparts already inside the black hole, contradicting the quantum principle of particles being entangled in pairs only. Page's theory could work if the particles inside the black hole were somehow identical to those outside. This conundrum led to the resurgence of wormholes, spacetime shortcuts proposed by Einstein and Rosen in 1935 as a possible connection between the inside and outside of a black hole. In 2012, Drs. Maldaceno and Susskind proposed a resolution combining spooky entanglement and wormholes. They suggested that these two phenomena were essentially the same, encapsulated in the formula ER equals sine EPR, referencing the authors of the two 1935 papers. This implies that, paradoxically, the outside of a black hole is the same as the inside, resembling a Klein bottle with only one surface. The idea of information being in two places simultaneously is a mind-boggling aspect of quantum physics, similar to light behaving as both a wave and a particle. According to Caltech physicist and quantum computing expert John Preskill, if the interior and exterior of a black hole are linked by wormholes, information could traverse these wormholes in either direction. He suggested that by interacting with a black hole's radiation, it might be possible to affect its interior, an idea he admitted sounds implausible. Physicist Ahmed Almheri further illustrated this by stating that manipulating radiation escaping a black hole could theoretically create a cat inside it. In 2019, two groups of theorists, including Jeff Pennington and Netta Engelhardt, among others, provided calculations supporting Dr. Page's theory that information passing through wormholes would align with his predictions. Pennington concluded that if a theory of gravity includes wormholes, information can emerge from it. Otherwise, it cannot. This contrasts with Hawking's original theory, which did not consider wormholes. Despite this progress, not everyone in the scientific community accepts this theory, and its experimental verification remains a challenge. While particle accelerators may never be powerful enough to create black holes for laboratory study, some researchers hope to simulate black holes and wormholes using quantum computers. Regardless of the theory's accuracy, it's crucial to note that neither wormholes nor entanglement can transmit anything, including messages or humans, faster than the speed of light, ruling out time travel. The oddities of these phenomena only become evident retrospectively, when observers compare notes using classical physics, which adheres to Einstein's speed limit. As Dr. Susskind humorously notes, this means one cannot make a cat emerge from a black hole faster than light. Since 1974, theoretical physics has faced a significant challenge due to Stephen Hawking's theory that black holes destroy information. Hawking suggested that black holes could slowly evaporate, turning themselves and everything they absorb into a vague cloud of radiation. This seemed to imply that information about what the black hole consumed was lost, going against a key principle of physics. This issue remained unsolved for almost 50 years, until a breakthrough emerged in 2019. The solution hinges on a new understanding of spacetime and its reconfiguration via quantum entanglement. This concept introduces the notion that a segment of the black hole's interior, known as the island, might actually be on its outside. Understanding this idea requires looking at the fundamental nature of black holes. Black holes form when a large amount of matter is squeezed into a very small space, causing spacetime to collapse. This results in a point known as the singularity, where time and space stop making sense. The event horizon, the boundary of the black hole, marks the point of no return. Anything that crosses this boundary, including light, cannot escape. The issue becomes more complex when quantum mechanics comes into play. Quantum theory shows that black holes aren't just consuming energy, they eventually give it back as Hawking radiation. This radiation, squeezed from the vacuum near the event horizon, seems to come from nothing. In quantum theory, what looks like empty space is actually full of particles like electrons and photons, which exist in pairs and help hold spacetime together. However, at the event horizon of a black hole, these particle pairs get separated. One falls into the black hole, while the other escapes as Hawking radiation. This process makes the black hole lose mass over time. From the outside, it looks like the black hole is slowly disappearing, similar to how burning a book turns it into light and ash, seemingly preserving the information. The real puzzle starts with the separation of these particle pairs at the event horizon. Despite being apart, they remain connected through quantum entanglement. Albert Einstein, Boris Podolsky, and Nathan Rosen first brought up entanglement as a criticism of quantum mechanics, with Einstein famously calling it spooky. For example, imagine two coins that are connected in such a way that if one is heads, the other is also heads, and the same for tails. They're not in both states at once, but their outcomes are perfectly linked. This entanglement puzzled scientists because it seemed like the coins could influence each other instantly, even if they were light years apart. Einstein was both right and wrong about entanglement. He correctly saw its importance in quantum mechanics, but misunderstood that the linked outcomes of entangled particles don't mean one causes the other. Quantum mechanics, it turns out, permits a level of correlation beyond our conventional understanding. Hawking radiation, composed of one half of entangled particle pairs, exits black holes in a state of complete randomness. If these particles were akin to coins, their observation as heads or tails would be equally probable. Consequently, the random nature of this radiation renders it useless for deducing any specifics about the black hole's contents. In essence, an evaporating black hole acts like an advanced information shredder, but unlike its mechanical counterpart, it performs this task thoroughly. The randomness, or lack of information, in Hawking radiation can be quantified by examining the entanglement between the radiation and the black hole. Since one half of an entangled pair is always random, and these are the only parts left after complete evaporation, the randomness increases with each particle of Hawking radiation emitted. This increase in randomness, or entanglement entropy, continues to grow until the black hole vanishes entirely. Contrast this with a scenario where information is preserved, like a burning book. In such cases, entropy might initially rise, but must eventually peak and then decline to zero as the process concludes. This concept is easier to grasp with a deck of cards analogy. Imagine being dealt cards from a standard 52-card deck, face down. The entropy, or your uncertainty about the card's identity, starts at 52 for one card. As more cards are dealt, entropy increases, peaking at around 500 trillion possibilities for 26 cards. However, as you receive more cards, the entropy decreases, eventually returning to 52 with 51 cards. When you have the full deck, entropy drops to zero as you know exactly what you have. This rise and fall of entropy, known as the page curve, is typical of all standard quantum mechanical systems. The point where entropy peaks and then starts to decrease is referred to as the page time. The loss of information within black holes presented a significant problem for physics, as quantum mechanics dictates that information cannot be destroyed. This conflict is at the heart of the famous information paradox, where the introduction of quantum mechanics into black hole descriptions leads to a seemingly insurmountable contradiction. Resolving this paradox required a more comprehensive understanding of quantum gravitational physics to produce the page curve for Hawking radiation, a task that proved to be challenging. The real challenge lay in the fact that minor adjustments to the evaporation process were insufficient to generate the Page curve and reduce entropy back to zero. A radical rethinking of the black hole's structure was necessary. In a 2013 paper, co-authored by Donald Marolf, the late Joseph Polchinski, and Jamie Sully, various modifications to the concept of evaporating black holes were explored through a series of thought experiments. The conclusion was that to preserve information integrity, one of two drastic changes was needed. Either physics must allow for instant information transfer, or a new process must emerge at a certain point in the black hole's evaporation. The first option, introducing non-locality into physics, was too extreme, so the focus shifted to the second. This new approach helped preserve information, but led to another paradox. Remember, the entanglement across the horizon results from the presence of empty space, maintained by a sea of entangled particle pairs. Breaking this entanglement would mean creating a barrier of high-energy particles, which was termed the firewall. Such a firewall at the horizon would prevent anything from entering the black hole, vaporizing it upon contact instead. At the Page time, the black hole would abruptly lose its interior, and spacetime would end not at the deep singularity, but right at the event horizon. This dilemma, known as the firewall paradox, suggested that any solution to the information paradox would drastically change our understanding of black holes. The solution came when it was realized that applying quantum mechanics to the spacetime of black holes, not just their matter, was necessary. While quantum effects on spacetime are typically minimal, they could be amplified by the significant entanglement produced during evaporation. To explore the quantum nature of spacetime, Richard Feynman's path integral technique from quantum mechanics was used. This approach is based on the quantum theory principle that particles, and spacetime itself, can exist in many different states simultaneously. It was found that the strong entanglement between Hawking radiation and black holes could increase the chance of temporary wormholes forming between black holes. These wormholes swap parts of the black hole's interiors, called islands, changing how we calculate the entanglement entropy between a black hole and its Hawking radiation. This new calculation, which treats the island as part of the exterior Hawking radiation, solves two paradoxes. It suggests that we should think of part of the black hole's interior as being on the outside, and it shows how black holes can preserve information, producing the Page curve. In summary, the information paradox arose from the conflict between black holes trapping information and quantum mechanics requiring information flow. Simple resolutions to this tension led to drastic changes in our understanding of black holes. However, the subtle yet significant effects of fluctuating wormholes changed the entire picture. We now have a consistent view that allows a black hole to maintain its structure as predicted by general relativity, with an underlying non-locality. This non-locality suggests that part of the black hole's interior is actually part of the outside, allowing information to escape not by passing the event horizon, but by being part of the island. While this is a significant breakthrough, it's just the start of understanding the implications of spacetime wormholes and the island formula. These concepts show that gravity can work with quantum mechanics, using entanglement to achieve non-locality, a concept as unsettling as the entanglement that once troubled Einstein. In a way, Einstein was right all along. Black holes commonly originate from one of two principal mechanisms. The first involves a massive star undergoing a catastrophic collapse, where its core becomes inundated with an excessive amount of matter. This process often occurs in stars significantly larger than our Sun, where the intense gravitational forces cause the core to compress and eventually collapse under its own weight. As the core collapses, it reaches a point where the density and gravitational pull become so extreme that a black hole is formed. The second mechanism occurs in neutron stars, remnants of supernova explosions, which are already incredibly dense. When a neutron star, typically about 1.4 times the mass of the Sun, continues to accumulate mass from its surroundings or a companion star in a binary system, it can reach a critical mass threshold between 2.1 to 3 solar masses. Upon crossing this threshold, the neutron star undergoes a similar collapse, resulting in the formation of a black hole. This process is often accompanied by the emission of intense gravitational waves, a phenomenon predicted by Einstein's theory of general relativity and recently confirmed by observations. These gravitational waves are ripples in the fabric of spacetime, generated by the violent movements of these massive objects. providing astronomers with crucial insights into these enigmatic and powerful cosmic events. The most straightforward pathway to a black hole's creation is observed in the final stages of a star of considerable mass. In these stars, the heavier elements resulting from nuclear fusion gradually build up in the core. For stars of sufficient size, these elements eventually act as new fuel, leading to the formation of even heavier elements in the core. In the star's final moments, its silicon core undergoes fusion, rapidly producing iron. This iron core expands in mass until it either exceeds the Chandrasekhar limit or its iron nuclei are shattered by high-energy photons, leading to its collapse. This collapse initiates a shock wave as the core recoils from its compressed state. The shock wave momentarily pauses. During this brief interval, neutrinos generated in the core gather behind the shock wave, eventually providing enough energy to propel it forward, triggering a supernova. Simultaneously, as this buildup occurs, other materials that have already been pushed by the shock wave continue to pile up on the core, now a proto-neutron star. If the core gains enough mass, it becomes unstable due to gravity and collapses into a black hole. If the core transforms into a black hole before the shock wave gains momentum again, neutrino production halts, and any existing neutrinos vanish into the event horizon. This sudden drop in pressure causes the entire star to implode without an explosion. For stars with a mass range of 25 to 40 solar masses, the shock wave reactivates before the core reaches a point of gravitational instability. This leads to a supernova explosion that ultimately results in a black hole, although this explosion is comparatively weaker since the core can no longer generate additional neutrinos to enhance the supernova. An intriguing question is why some stars successfully reignite their shockwaves while others do not. Stars with masses significantly exceeding 40 solar masses gather so much material in their collapsed cores that a black hole forms before the shockwave can resume. As these stars collapse, their internal matter is gradually drawn into the event horizon, and eventually the entire star is engulfed by the black hole within a few hours. Not all stars of a given mass end up with the same fate. Two stars of identical mass can produce different remnants, influenced primarily by a factor known as metallicity. Metallicity, in the context of stars, refers to the proportion of elements heavier than hydrogen or helium in a star's composition. For example, the Sun's metallicity is around 1.5%, meaning 1.5% of its mass consists of elements heavier than helium. When astrophysicists discuss a star's mass, they refer to its initial mass, which is the mass of the star when hydrogen fusion begins in its core. Similarly, initial composition refers to the star's elemental makeup at its formation. Observing a diagram that shows higher metallicities leading to fewer black holes, it's important to note that this refers to the star's metallicity at birth, not at the time of its collapse. This leads to the question, why does a higher metallicity decrease the likelihood of black hole formation? The intense energy from nuclear fusion and thermal collisions within a star generates a vast number of photons. These photons spend hundreds of thousands of years being absorbed or bouncing around inside the star. Each collision exerts a tiny amount of radiative pressure, gently pushing the star's matter outward. Atoms with larger nuclei, or those with more metallic content, possess a stronger positive charge due to their higher proton count. This attracts more electrons, creating a broader range of energy states for these electrons, allowing them to absorb a wider range of photon energies. In simpler terms, gases with a higher metal content are less transparent and more difficult for light to penetrate compared to gases composed mainly of hydrogen and helium. This results in more photon collisions, exerting greater outward radiative force. The trapped heat leads to stronger convection currents within the star, which, combined with increased solar winds, causes the star to shed material over time. A massive star goes through various stages, influenced by metallicity, affecting its mass loss over time. Therefore, a higher metallicity causes a star to shed more mass during its lifetime, especially in its final stages, reducing the likelihood of it becoming a black hole. If a star's demise results in a neutron star, there's still a chance for a black hole to form. Neutron stars typically have a mass around 1.4 times that of the Sun, which is significantly less than the 2.1 solar mass threshold mentioned earlier. The most feasible way for a neutron star to accumulate enough mass to reach this threshold is through interaction with another celestial body, most likely in a binary system. Binary systems consist of two celestial bodies, gravitationally bound and orbiting a shared center of mass. In the early universe, neutron stars were often found in binary systems, as regions with sufficient gas to form one large star usually had enough to form a second star nearby. Whenever mass accelerates, it emits gravitational waves. Thus, orbiting objects gradually lose a tiny amount of energy as these waves dissipate. The amount of energy lost is heavily dependent on the distance between the orbiting bodies. To understand the gradual nature and duration of this orbital decay, consider two equal mass neutron stars orbiting each other at a distance of 2 million kilometers, about 5 times the distance from the Earth to the Moon. It would take approximately 2 billion years for these stars to merge at this distance. Although this process starts off weak and slow, especially for orbits much smaller than we're used to, 2 billion years is still shorter than the age of the universe. Hence, many such mergers have already occurred, and many more are still billions of years away. However, the final stages of orbital decay in binary neutron star systems are particularly intriguing. Unlike normal stars, which can't orbit too closely without colliding, neutron stars, with their dense, compact 10-kilometer radii, can achieve incredibly close orbits. Take, for example, the Hulse-Taylor binary system, which is also separated by about 2 million kilometers. However, its orbit is elliptical, ranging from roughly 3 million kilometers to just under 750,000 kilometers. These are two objects, each heavier than the Sun, orbiting within a distance slightly larger than the Sun's radius. If they were actual suns, their proximity would be astonishing. Despite being so close, it's estimated that they will take another 300 million years to merge. Accelerating to the final hour before their merger, the neutron stars are about 1,000 kilometers apart, completing 3 orbits every second at 6% the speed of light. Each orbit at this stage releases energy equivalent to what the Sun produces in 500,000 years into gravitational waves. 1 minute before the merger, the stars are about 360 kilometers apart, orbiting 14 times per second at 11% the speed of light. Over the past 2 billion years, they have emitted approximately 7 times 10 to the 44th joules of energy, equivalent to the energy output of 5 suns over their lifetimes. This astonishing amount is less than a tenth of what will be released in the final minute. It's only during this last minute that the gravitational waves produced are strong enough to be detected on Earth. In the final second before merging, the neutron stars are still 100 kilometers apart, moving at about 20% the speed of light. The extreme tidal forces at this stage start to deform the neutron stars. When they are 30 to 40 kilometers apart, they are torn apart, and their masses collide at the center. This final implosion releases gravitational energy comparable to that of a core collapse supernova, about 80 times the Sun's lifetime energy output. However, unlike a supernova, which primarily emits neutrinos, this energy is predominantly released as gravitational waves. This dramatic occurrence is known as a kilonova. Kilonovae are about 1 to 10% as bright as core collapse supernovae. They are believed to be a primary source of the heaviest elements in the universe and are associated with short-duration gamma-ray bursts lasting a few seconds. While the specifics are fascinating, they warrant a separate detailed discussion. Ultimately, the aftermath of such an event can result in a rapidly spinning black hole. The final, somewhat less dramatic way a black hole can form is when a neutron star is part of a binary system with a regular star. As the companion star expands in its later life stages, its outer layers may become more attracted to the neutron star's gravity than to its own star. This leads to the transfer of matter to the neutron star through a process known as Roche-Lobe overflow. This transferred material can increase the neutron star's mass, but the efficiency of this process is not well understood. X-ray bursts observed during such accretion events suggest that material reaching the neutron star's surface may detonate and potentially be ejected. If enough material accumulates, the neutron star may reach a point of gravitational instability and collapse into a black hole. However, whether this actually occurs remains uncertain. Observations of black holes in binary systems indicate a lower mass limit of about 4 to 5 solar masses, suggesting that black holes formed through accretion are rare. Yet, it's possible that lower mass black holes are simply harder to detect, leaving the reality of such occurrences unclear. In summary, black holes are the remnants of massive stars, either directly formed from the collapse and accumulation of their iron cores, or from the merger of neutron stars left behind by supernovae with other stellar objects. It's theorized that in the early universe, gas could directly collapse into an intermediate mass black hole, ranging from 1,000 to 10,000 solar masses, without undergoing the fusion process typical of a star's core. This, however, is a topic for another discussion. In the realm of astrophysics and cosmology, black holes are often discussed as enigmatic and complex phenomena. However, a fundamental aspect of their nature is that they are four-dimensional objects. This four-dimensionality encompasses the three spatial dimensions: length, width, and height, as well as time, the fourth dimension. These dimensions are interwoven into a unified fabric known as spacetime, which forms the foundational structure of the universe. The concept of a black hole as a four-dimensional object might seem exotic, but in reality, it aligns with the nature of all physical objects in the universe. For example, consider everyday objects like a desk. Spatially, a desk occupies a certain volume, extending in the x, y, and z directions, corresponding to its width, length, and height. However, it also has a temporal dimension. Its existence spans from the time of its creation to its eventual destruction. This temporal extension, or lifetime, is as integral to the desk's existence as its spatial dimensions. Thus, the desk, like all physical objects, occupies a four-dimensional volume in spacetime. The inclusion of time as the fourth dimension is not merely a theoretical construct. It has significant physical implications, especially when viewed through the lens of relativity. Objects observed in one reference frame to have a large spatial dimension, and a small temporal dimension may appear differently in another frame, with a contracted spatial dimension and an expanded temporal dimension. This phenomenon, resulting from relativistic effects like length contraction and time dilation, underscores the importance of considering time as an integral dimension of spacetime. Black holes, while sharing the four-dimensional nature of objects like chairs or trees, exhibit unique characteristics that distinguish them. A black hole is a region where spacetime is so intensely warped that nothing, not even light, can escape its gravitational pull. This extreme warping of spacetime means that, to an observer at a distance, the black hole appears as a void in spacetime, with the event horizon acting as a perceived boundary. From this vantage point, a black hole seems to lack an inside, with all its mass and energy concentrated at the event horizon. However, this perception is relative and depends on the observer's position. Closer to or inside the event horizon, spacetime continues, and the black hole does possess an interior. These differing observations are reconcilable due to the relativistic nature of spacetime. The shape of a black hole in four-dimensional spacetime is another aspect of interest. A non-rotating black hole is spherical, with its event horizon forming a perfect sphere, extending linearly through time. This spherical shape is intuitive, considering a black hole as a collapsed star, trapping all its light. A rotating black hole, more common in reality, is not perfectly spherical, but slightly flattened along its axis of rotation, forming an oblate spheroid. This shape also extends linearly through time. The degree of flattening depends on the black hole's rotation rate. Slowly, rotating black holes can be approximated as non-rotating, while rapidly rotating ones exhibit more pronounced oblateness. If a black hole is undergoing changes, such as uneven accretion of matter, its shape may deviate from perfect sphericity, but these deviations are generally minor. In summary, a black hole is a four-dimensional entity, extending through both space and time. Its shape, whether spherical or nearly spherical, is a manifestation of its four-dimensional nature. This understanding of black holes as four-dimensional objects aligns with the broader concept that all physical entities in the universe, from the smallest particles to the largest celestial bodies, exist within the four-dimensional framework of spacetime. It's important to note that fundamental particles, such as electrons, often behave like point particles, seemingly having zero dimensions in space. However, this is an oversimplification. In quantum mechanics, simple concepts like size and volume do not have straightforward meanings. An electron, for instance, does not have a fixed, definite, non-zero physical radius. In many experiments, it behaves as if it had a radius of zero, but it also has a finite mass, suggesting it cannot have an actual radius of zero. If it did, it would become a black hole, which is not the case. This apparent contradiction is resolved by understanding that quantum particles do not have a definite radius. Instead, they exist as fluctuating, ambiguous, smeared-out probability clouds of matter and energy. Thus, fundamental particles are not one-dimensional, but are four-dimensional objects within the space-time continuum. When considering the shape of a black hole, common imagery might bring to mind either the iconic funnel shape or the depiction of a dark sphere surrounded by a glowing disk of matter and light, similar to the portrayal in the movie Interstellar. This representation is a visually stunning interpretation of what a supermassive black hole and its surrounding accretion disk might look like from a close perspective. However, to accurately answer the question, what shape is a black hole? One must venture beyond the familiar three-dimensional understanding and contemplate an array of shapes that are beyond the grasp of the human imagination. Traditionally, black holes have been depicted as funnel-shaped in various artistic renditions, attempting to illustrate their profound impact on the surrounding space and time. This representation, while useful for conceptual understanding, simplifies the complex nature of spacetime, which encompasses more dimensions than can be visually represented in two-dimensional media. In these artistic depictions, the actual shape of the black hole is represented not by the entire funnel, but by a specific circular section at the funnel's throat. This circle symbolizes the event horizon, the infamous point of no return for a black hole. Since anything beyond the event horizon is imperceptible, the event horizon serves as the closest approximation to a physical boundary or surface of a black hole. Thus, discussions about the shape of a black hole are essentially focused on the shape of its event horizon. When this concept is expanded beyond two dimensions, the circle at the funnel's throat transforms into a sphere, leading to the conclusion that black holes are spherical in nature. However, Stephen Hawking, renowned for his work on black holes, suggested that the event horizon of a black hole need not be strictly spherical. Instead, it must adhere to being topologically spherical. A topological sphere is any shape that can morph into a sphere without altering the number of holes it contains. For example, a hollow ball of clay, when deformed, might lose its perfect spherical shape, but remains topologically spherical. Similarly, any shape achieved by manipulating a sphere, such as a heart shape, still retains this topological characteristic. This concept implies that it is normal, and perhaps even typical, for black holes to be ellipsoidal in shape, much like how the Earth's rotation causes it to deviate slightly from a perfect sphere. However, Hawking's theories are based on the assumption of a three-dimensional space. If the universe contains more than three spatial dimensions, as suggested by research in 2002, the shape of a black hole could be far more complex. In a four-dimensional space, a spinning black hole could theoretically resemble a higher dimensional structure, akin to a donut, termed a black ring. This concept challenges traditional perceptions of black holes, as a donut and a sphere possess distinct topologies. A sphere cannot be transformed into a donut without fundamentally altering its structure, such as by creating a hole. Observations from the Event Horizon Telescope have revealed donut-like shapes in the vicinity of black holes, but these formations result from the light surrounding the black hole rather than the black hole itself. The dark central area in these images is the shadow cast by the event horizon. The discovery of an actual donut-shaped black hole would be groundbreaking, potentially indicating the presence of a fourth spatial dimension. In addition to the possibility of black rings, another complex topology has been proposed: the lens space. This concept, introduced in 2006, posits that in a universe with four spatial dimensions, a black hole's event horizon could take the form of a lens space. Lens spaces are often described as folded-up spheres and represent a relatively simple topology after spheres. Understanding lens spaces requires delving into the concept of rotations that link multiple points on a shape. To illustrate this, one can use a simple hair tie marked with points that are 180 degrees apart. By twisting the hair tie, these points can be aligned, effectively collapsing the circle to half its original size. Further twists create different lens spaces, each tying together more points and further reducing the size of the circle. In a four-dimensional space, the event horizon of a black hole would be a three-dimensional lens space, involving more intricate folding, but based on the same principle of rotations. There are countless lens spaces that can be created, each with its unique configuration. Research in 2022 validated the mathematical legitimacy of black hole lens spaces in spaces with four or more dimensions. This research suggests an infinite variety of shapes for black holes, regardless of the number of dimensions in the universe, as long as it exceeds the currently known 3 dimensions. However, To support the existence of black lens structures, researchers had to introduce a type of exotic matter not currently accounted for in existing models of reality. This makes the hypothesis highly speculative and theoretical. To date, there is no observational evidence of non-spherical black holes, and the appearance of black rings or black lenses to human observers remains a matter of conjecture. Despite the speculative nature of these hypotheses, the possibility of such exotic shapes for black holes opens up exciting avenues for future scientific exploration and imaginative portrayals in science fiction. The exploration of these concepts not only challenges our understanding of black holes, but also expands our comprehension of the universe's fundamental structure and the nature of dimensions beyond our current knowledge. The field of astrophysics is captivated by one of its most enigmatic and intriguing subjects, black holes. These extraordinary cosmic entities are not just mere voids in space. They are regions where the very fabric of space and time intertwine in complex and bewildering ways. At the heart of this intrigue is the interplay between gravity, a fundamental force shaping the cosmos, and the principles of quantum mechanics, which govern the subatomic world. Black holes stand out because they are found at the centers of almost all known galaxies, including our own Milky Way. Intriguingly, these massive black holes seem to have a mysterious connection with the properties of their host galaxies, a phenomenon that continues to puzzle astronomers and physicists alike. This unique relationship suggests that black holes are not just isolated objects, but are integral to the broader cosmic narrative, influencing and reflecting the nature of the universe itself. Defining a black hole is a task that delves into the very extremes of physics. A black hole is so named because it is a region from which nothing can escape, not even light, the fastest thing in the universe. This inescapability is what renders the black hole black to observers. Surrounding this impenetrable region is a boundary known as the event horizon. This is not just a physical boundary, but also a threshold where the known laws of physics start to behave in unfamiliar ways. The event horizon marks the point beyond which light and matter cannot return to the observable universe. It's a realm where the conventional understanding of space and time begins to break down, leading to bizarre phenomena that challenge our understanding of reality as predicted by Einstein's theory of general relativity. The event horizon of a black hole is not just a theoretical construct, but a key to unlocking the mysteries of these cosmic giants. To probe this frontier, scientists employ sophisticated simulations, akin to the methods used by meteorologists to predict weather patterns on Earth. These simulations involve solving complex hydrodynamic equations, known as the Navier-Stokes equations, on powerful computers. By iterating these calculations step by step, scientists can model how gas clouds behave in the extreme gravitational environment near a black hole. This process helps in visualizing how the density, shape, and velocity of these clouds evolve over time as they interact with the black hole's immense gravitational pull. The center of our galaxy, where the supermassive black hole resides, presents a particularly challenging environment for these studies. The complexity of this region means that many variables need to be considered to accurately simulate the behavior of matter near the black hole. In this endeavor, the collaboration between theorists and observers is crucial. Theorists rely on observational data to refine their models and ensure they accurately reflect the reality of the cosmos. This synergy between theory and observation is a cornerstone of modern astrophysics, allowing for a more comprehensive understanding of complex astronomical phenomena. One of the landmark observations in recent years was the discovery of a gas cloud near the center of our galaxy in 2012. Initially, this cloud was compact and spheroidal. However, simulations predicted that as it neared the black hole, the intense gravitational forces would stretch and distort it into a long spaghetti-like structure. This phenomenon, known as spaghettification, was indeed observed by astronomers, validating the predictions and demonstrating the power of computational astrophysics. The journey of this gas cloud was expected to culminate in its eventual accretion onto the black hole, an event that would provide unprecedented insights into the behavior of matter at the edge of the event horizon. However, the story took an unexpected turn. The cloud, after stretching into a spaghetti-like form, did not behave as the initial models predicted. Instead of compactifying and accelerating towards the black hole, it showed signs of reforming into a more compact structure. This puzzling behavior led researchers to revisit their models, incorporating additional factors such as the cloud's magnetic field and its composition, which included numerous small droplets. These refinements in the model suggested that the accretion event might still occur, but at a later time than initially predicted. This ongoing saga of the gas cloud offers a valuable opportunity for astronomers to observe and understand the complex dynamics at play near a black hole's event horizon. The event horizon itself is a fascinating subject of study, representing a convergence point of two of the most important theories in physics: general relativity and quantum mechanics. General relativity, which describes the gravitational behavior of large objects like stars and galaxies, predicts that the event horizon is an infinitely thin boundary. In contrast, quantum mechanics, which governs the behavior of particles at the smallest scales, suggests that, at the scale of the event horizon, quantum effects cannot be ignored. This dichotomy presents a unique opportunity to observe and perhaps understand the elusive theory of quantum gravity, which seeks to unify these two fundamental but currently incompatible frameworks of physics. The quest to understand black holes and their event horizons has led to the development of ambitious observational projects like the Event Horizon Telescope, EHT. The EHT is a global network of radio telescopes that, when used in conjunction, effectively creates a planet-sized telescope capable of resolving features as small as a black hole's event horizon. This remarkable instrument is expected to provide groundbreaking insights into the nature of black holes. One of the key phenomena that scientists hope to observe with the EHT is the formation of massive jets of material that are ejected from the vicinity of the event horizon. These jets are not only spectacular to behold, but also play a significant role in the evolution of galaxies. They can extend well beyond the size of the galaxy itself and potentially influence the formation of stars and the distribution of matter within the galaxy. The relationship between a galaxy and its central black hole is one of the most intriguing aspects of modern astrophysics. Observations have shown a strong correlation between the mass of a galaxy's central black hole and various properties of the galaxy itself. This suggests that these seemingly isolated objects have a profound influence on their host galaxies, a phenomenon that is not yet fully understood. By studying the interaction of gas clouds with black holes and observing the dynamics near the event horizon, scientists hope to unravel this mystery. Furthermore, the study of supermassive black holes, like the one at the center of our galaxy, raises fundamental questions about their origins. These black holes are so massive that they cannot have formed from the collapse of a single star. Understanding how they accumulated such immense amounts of matter and what processes led to their formation are key questions that drive current research. The answers to these questions could shed light on the early stages of galaxy formation and the evolution of the universe itself. In summary, the study of black holes, particularly the exploration of the event horizon, is a journey that intertwines the most extreme aspects of physics. It challenges our understanding of the universe, from the largest scales of galaxies down to the fundamental laws that govern the fabric of space and time. The next decade promises to be a golden era for black hole research, with potential discoveries that could reshape our understanding of the cosmos and unlock new frontiers in physics. In a hypothetical scenario, where a point in space emits light uniformly in all directions, this emission results in the creation of an expanding three-dimensional region. This region's boundary represents the maximum distance that light has traveled from the source over a given period, underscoring the principle that nothing can move faster than the speed of light. When observed in a two-dimensional context, this three-dimensional expansion is analogous to an expanding circle. Analyzing this phenomenon in a step-by-step manner, one can conceptualize a diagram where the expanding region of light is depicted as a cone-shaped structure. This cone, which expands over time, serves as a representation of the progression of time itself. The sides of this cone are set at a 45-degree angle, a depiction that correlates with the uniform speed of light, which dictates that light covers a consistent distance in a specific time frame. In physics, this cone-shaped representation is known as a light cone. With the passage of time, the light cone continues to expand at the speed of light, including everything within its expanding range. In the realm of relativity, these light cones are instrumental in deciphering the universe's structure, especially in delineating the boundaries of cause and effect. To illustrate, envisage an event occurring at a cosmic distance, like a supernova explosion. This distant cataclysm cannot influence us until the moment its light cone intersects with Earth. Prior to this intersection, we are oblivious to the event, constrained by the universal truth that nothing surpasses the speed of light. It's only when we enter this light cone that we begin to perceive and feel the supernova's ramifications on Earth. This phenomenon underlines causality, the principle that one event can impact another, bound by the velocity of light. Crucially, light cones accentuate the stark contrast between time and space. How do we differentiate time from space? In the realm of space, movement is fluid and unrestricted. We can venture in any direction, reverse our course, or even follow a path that loops back on itself. However, in the dimension of time, all entities are inexorably driven in a singular direction. In time, reversal is a concept of fantasy. Our movement is unidirectionally from the past towards the future. The concept of light cones vividly manifests this distinction. In space, direction is a matter of choice. But in time, the successive light cones compel us to perpetually move forward. We are trapped within these light cones, unable to turn back. This unique property permits us to define time in the context of relativity. Time is essentially the orientation of the light cones. It's this unidirectional path we cannot reverse. It's the trajectory where all permissible movements point, and where our future inevitably unfolds. Space, conversely, encompasses all other directions, lying perpendicular to the path of time. In an alternate universe where gravity is absent, the structure of space-time remains unchanged and linear. In this scenario, time and space form a symmetrical, rectilinear grid, a concept central to our understanding of physics. Light cones, which represent the potential paths that light can travel in space-time, align uniformly in such a space. This uniform alignment allows for a global definition of time, typically visualized as moving linearly from one side of the diagram to the other, for instance, from left to right. Introducing a massive object like Earth into this universe changes this structure dramatically. An apple, when released, falls towards Earth, driven by the planet's gravitational pull. This phenomenon illustrates that gravity's influence extends beyond physical matter, affecting the path of light as well. If the apple were continuously emitting light, these paths of light would also bend towards Earth. Near a massive object, the uniform alignment of light cones is disrupted, bending increasingly under the influence of gravity. This bending of light cones near massive objects is a crucial aspect of Einstein's theory of general relativity, which suggests that the presence of mass and energy warps the fabric of spacetime. As the mass of an object increases, its impact on bending spacetime becomes more significant. In the case of an extremely massive yet compact object, this effect is so intense that it creates a region where all light cones point inward. This effect describes the formation of a black hole, a region in space where the curvature of spacetime is so extreme that all paths, including those of light, are inwardly directed. Below a certain point, known as the event horizon, this inward pull becomes so strong that escape becomes impossible, even for light. A black hole can be visualized as a spherical region or a bubble in spacetime, where everything, including light, is inexorably drawn towards its center. In a two-dimensional representation, a black hole appears as a circle, tracing a cylinder through the expanse of spacetime. The event horizon of a black hole is a crucial boundary. Above it, light may still escape, but below this horizon, all light is captured. Inside a black hole, the orientation of light cones, and consequently the direction of time itself, is altered to point towards the center of the black hole. To truly grasp the essence of a black hole, it is insightful to consider two disparate viewpoints, that of an astronaut succumbing to the black hole's grasp, and that of a distant observer, stationed far away. For the remote observer, the influence of gravity is negligible, and in his vicinity, the fabric of spacetime remains undistorted. For this observer, time flows linearly from left to right. The horizon of the black hole, from his perspective, appears static, tracing an unchanging line from the past into the future. However, let's shift to the perspective of the astronaut in descent. As she approaches the horizon, the concepts of time and space become increasingly distorted, molded by the black hole's overwhelming presence. Upon reaching the horizon, unbeknownst to the astronaut, time and space are inclined at a critical 45-degree angle. From the astronaut's viewpoint, the horizon is not a linear boundary stretching from past to future. Rather, It ascends diagonally at 45 degrees, mirroring the surface of a light cone. While the distant observer perceives the black hole as a stationary entity, for the astronaut at the brink, time and space are skewed in such a manner that the black hole mimics the properties of a light cone, elucidating why escape is a futile endeavor. As she crosses the horizon, the constructs of time and space appear inverted compared to the external world. Time now points downwards, a direction previously associated with spatial movement. The horizon of the black hole transitions from a spatial boundary to a moment in our past, and the center of the black hole transforms from a spatial point to an event in our future, an inescapable destiny. Beneath the horizon, all objects inevitably plummet, for it is in this direction that their future is predetermined. When a massive star implodes, it emits one final luminous burst, a last-ditch effort to expand. But within a space-time contorted by the star's mass, this bubble appears motionless from an external perspective. A black hole has emerged. It is a light cone, rendered static by the warping of space-time. If we were to reorient this depiction, we recover a universal direction of time, flowing linearly from left to right. In this realigned diagram, it becomes explicitly clear that the horizon of the black hole forms a light cone, originating from the collapsing star, a structure from which escape is unattainable. Once we traverse below the horizon, our fate is sealed. A collision with the center of the black hole is inevitable, a locale where the curvature intensifies to such a degree that our current scientific models cease to function. The core of the black hole, thus, represents an event in the imminent future. Ultimately, if we compress this diagram, we arrive at a Penrose diagram, a schematic representation where the exterior and interior of the black hole constitute two distinct realms. The moment we cross the horizon, the remainder of the universe is relegated to our past, forever inaccessible. Our sole conceivable future is a relentless descent, all the way to the singularity. Colossal black holes, whose masses dwarf our Sun by billions of times, have long been a source of intrigue and perplexity for astronomers and astrophysicists. These astronomical marvels not only challenge our existing theories, but also raise questions about the very mechanisms of cosmic evolution. Theoretically, the age of the universe, estimated since the Big Bang, seems insufficient for such massive entities to have formed naturally. Typically, black holes are known to form when a massive star ends its life cycle in a supernova explosion, collapsing under its own gravitational force. These resultant black holes are generally about 5 to 50 times the mass of our Sun. However, the enigma intensifies when considering supermassive black holes, which range from 100,000 to several billion times the mass of our Sun. In recent decades, particularly over the past 10 years, the discovery of numerous supermassive black holes, each with a mass exceeding 1 billion times that of the Sun, has been a revelation. Found at vast cosmic distances, these discoveries indicate that they formed within the first 800 million years, post-Big Bang. The existence of such massive black holes in the universe's nascent stages poses significant challenges to our understanding of black hole formation and growth. These gargantuan structures, emerging shortly after the universe's birth, are located at the centers of most galaxies, including our own Milky Way. Remarkably, they underwent rapid development in relatively brief periods before their growth abruptly plateaued. The role of these supermassive black holes in shaping the universe's formation and evolution is undeniably critical, yet the mechanisms behind their rapid and massive growth remain a puzzle to the scientific community. The prevailing view among astrophysicists is that these supermassive black holes evolved from smaller, primordial black holes. Some of these cosmic giants were already in place a mere 690 million years after the universe's inception, a duration too brief on a cosmic timescale for a star to form, collapse into a black hole, and then accumulate enough mass to reach supermassive proportions. To achieve such immense sizes, these black holes must have engaged in the relentless absorption of vast amounts of gas over billions of years, engulfing any matter within their gravitational influence. This process of accretion makes them observable. As they ingest material from their host galaxy's cores, this matter forms an accretion disk that continuously feeds the black hole. The intense heat generated in this process emits copious amounts of X-rays, detectable from billions of light-years away. Thus, when astronomers observe a significant X-ray source in space, It's indicative of massive quantities of gas being consumed by a supermassive black hole. However, for these black holes to have reached such gargantuan sizes, they must have started off larger than average, providing them with an initial advantage in their growth trajectory. The direct collapse theory posits that these ancient black holes attained substantial sizes without undergoing the typical supernova phase. In 2019, a groundbreaking study by researchers Shantanu Basu and Arpan Das from Western University in Ontario, Canada, lent support to this theory. Utilizing a novel mathematical model, they analyzed the mass function of supermassive black holes that formed within a specific period and underwent rapid mass growth. Their hypothesis suggests that these black holes could have originated from a chain reaction process. The genesis of these initial black hole seeds is still a mystery, but the researchers propose a plausible subsequent process. They theorize that as each nascent black hole absorbed matter, it emitted energy, consequently heating up surrounding gas clouds. These heated gas clouds would collapse more easily than their cooler counterparts. Each significant absorption of matter by the black hole would result in more energy emission, heating additional gas clouds in a cascading effect. However, this chain reaction eventually came to an end. As more black holes, stars, and galaxies formed, emitting energy and light, they caused the surrounding gas clouds to dissipate. The cumulative radiation in the universe grew too intense, preventing large gas masses from collapsing directly, thus halting the process. The researchers estimate that this chain reaction persisted for about 150 million years. The Eddington rate, generally accepted as the growth limit for black holes, represents a balance between the outward force of radiation and the inward pull of gravity. In theory, this limit can be exceeded if the collapsing matter is sufficiently rapid. The new model proposes that during this chain reaction era, black holes were accumulating matter at a rate 3 times the Eddington limit. Basu and Das believe that their findings, when combined with future astronomical observations, could provide crucial insights into the formation history of these extraordinarily massive black holes in the early universe, potentially reshaping our understanding of cosmic evolution and the mysterious processes governing the growth of these enigmatic celestial giants. In the core of a black hole, all its mass is centralized at a singular point. This singularity is encased within an event horizon, a boundary where nothing can escape unless it surpasses the speed of light. Given that gravity propagates at light speed, the question arises, how does a black hole exert its gravitational influence outside this boundary? How is gravity able to break free from a black hole? Albert Einstein, in 1915, introduced his general theory of relativity. This theory reinterprets gravity as the result of space-time curvature rather than a conventional force. It predicted the existence of black holes, entities with such intense density that they warp space-time beyond the speed of light. According to Einstein's theory, objects exceeding this critical density are fated to collapse into a singular, infinitely dense point, encapsulated by the event horizon. General relativity also suggests that gravity has a finite speed. To align with the principles of his special theory of relativity, which governs the dynamics of motion relative to the speed of light, Einstein's equations incorporate the speed of light as a universal maximum for any causative influence, including the transmission of information. Gravitational effects, such as gravitational waves generated by certain movements in spacetime, also adhere to this light speed limit, a fact confirmed by observations of gravitational waves from neutron-star collisions arriving concurrently with their electromagnetic signals. However, a paradox arises. If gravity is bound by light speed and a black hole's mass is sequestered beneath the event horizon, how does it influence the universe beyond? Shouldn't the event horizon act as a shield against the black hole's gravitational effects? To address this, let's first consider Einstein's perspective. In general relativity, a black hole's gravity is unaffected by its event horizon. The gravitational field, the warp in space-time, exists separately from the mass that generates it. For instance, Earth's interaction with the Sun's gravity is with the local gravitational field, not directly with the Sun. Similarly, the area around a black hole responds to adjacent space-time, not the singularity itself. Imagine space as a rubber sheet distorted by a weight. Each part of the sheet is influenced by nearby sections, not directly by the weight. Alternatively, consider gravity as space flowing towards a mass. As an observer falls towards a black hole, They and their surrounding space reach the speed of light at the event horizon. This can be likened to a river accelerating towards a waterfall, where water at the brink is pulled by the current ahead. In general, relativity's black holes, gravity functions like this rubber sheet or flowing river. Each section of spacetime is influenced by its neighbor, not needing direct contact with the mass's source. However, general relativity may not be the ultimate theory, especially at the small scales or intense gravitational fields found at black hole singularities. Many physicists propose replacing it with a quantum gravity theory, where forces are mediated by particles, not spacetime geometry. For instance, electromagnetism operates through virtual photons. In quantum gravity, gravity might similarly involve gravitons. But how would gravitons escape a black hole's event horizon? In quantum field theory, virtual particles don't travel in a straightforward path. For example, when two electrons repel, they do so through the sum of all possible virtual photons, which don't follow a defined path but emerge from the broader electromagnetic field. So if gravity involves virtual gravitons, they wouldn't need to originate from the singularity or cross the event horizon. This understanding of gravity, whether as spacetime curvature or virtual gravitons, maintains our connection to the mass that created the gravitational field. Moreover, we can indirectly see a black hole's mass. As a star collapses into a black hole, it appears to freeze at the event horizon from an external viewpoint due to relativistic effects. The faintest signals of this collapse continue to reach the universe, imprinting the mass on the event horizon. Whether through spacetime curvature or virtual gravitons, we remain causally connected to the mass that generated the gravitational field. This connection extends to a black hole's electric charge as well. When a black hole absorbs charge, the electromagnetic field around it grows because we're interacting with the past charge, which appears frozen on the event horizon but still exerts influence. In a black hole, the concept of mass location is complex. Although we might think the mass is at the singularity, our interaction is with the local curvature of spacetime, shaped by past mass now perceived as being on the event horizon. This is because the gravitational field itself contributes to mass. To define mass consistently in general relativity, one must account for contributions extending infinitely from the black hole, making the mass of a black hole omnipresent. In summary, a black hole's gravity is not confined by its event horizon, as supported by various theoretical models. Proximity to a black hole inevitably leads to its gravitational pull, ensuring that your mass continues to affect regions outside the black hole in spacetime. The enigmatic core of a black hole, known as the singularity, stands as a profound mystery in astrophysics. It's a region where matter is thought to be compressed to an incredibly dense, infinitesimally small point, leading to a complete breakdown of conventional understandings of time and space. However, this concept of the singularity is largely theoretical. There's a consensus in the scientific community that something else must replace the traditional notion of the singularity, but the exact nature of this something else remains a topic of intense speculation and debate. Let's explore a few intriguing possibilities. One theory posits that deep within the confines of a black hole, matter doesn't actually condense into an infinitely small point. Instead, it's proposed that there exists a minimum limit to how small matter can be compressed, resulting in the smallest possible volume of matter. This hypothetical object is termed a Planck star, emerging from the theoretical framework of loop quantum gravity. Loop quantum gravity is an ambitious attempt to unify quantum mechanics and general relativity, leading to a quantum theory of gravity. In this theory, space and time are not continuous, but are instead made up of tiny, discrete units. These units are so incredibly small that to us, the macroscopic observers, space and time appear to be smooth and continuous. The concept of spacetime's granular nature, as suggested by loop quantum gravity, presents a couple of notable advantages. First, it fulfills the long-held goal of quantum mechanics to include gravity within a comprehensive physical theory. Second, and arguably more crucial, it naturally prevents the creation of singularities within black holes. When matter is compressed under the immense gravitational force of a collapsing star, it meets a fundamental resistance created by spacetime's discrete structure. This resistance is governed by the Planck length, which is approximately 1.68 times 10 to the negative 35th meters. Consequently, all the matter drawn into a black hole is compressed into a sphere that is slightly larger than this Planck scale. Although extremely small, this sphere is not infinitely small. As a result of this resistance to further compression, the matter within a black hole eventually undergoes a bounce, a theoretical explosion that causes the black hole to become a temporary phenomenon. However, due to the severe time dilation effects near black holes, as observed from our vantage point in the universe, this explosion would take an inconceivably long time, billions or even trillions of years. Another theoretical concept that challenges the existence of singularities is the gravastar. Unlike a black hole, a gravastar is theorized to contain dark energy instead of a singularity. Dark energy is an elusive force believed to permeate the fabric of spacetime, causing it to expand. This isn't purely speculative. Dark energy is currently understood to be driving the accelerated expansion of our universe. In the gravastar model, as matter approaches what would traditionally be the event horizon of a black hole, it's prevented from entering due to the repulsive force of the dark energy inside. This matter accumulates at the surface, creating a structure that, from an external perspective, mimics the gravitational effects of a black hole. However, the lack of a singularity means that the interior dynamics of a gravastar would be vastly different. Recent observations, particularly those involving the detection of gravitational waves from black hole mergers by facilities like LIGO and Virgo, have started to challenge the gravastar model. Theoretically, merging gravastars would produce different gravitational wave signatures than merging black holes. As our observational data grows, the likelihood of gravastars existing in our universe seems to diminish, although they have not been entirely ruled out. The ideas of Planck stars and gravastars, while fascinating, remain on the fringes of confirmed scientific understanding. The reality of their existence is still shrouded in doubt. It's possible that a more mundane, yet more scientifically grounded explanation for singularities exists, one that aligns with our evolving understanding of black holes. Traditional conceptions of singularities derive from the idea of stationary, non-rotating, uncharged black holes, essentially the simplest forms of black holes. However, real black holes in the universe are far more complex, particularly those that exhibit rotation. When a black hole rotates, the nature of the singularity changes dramatically. The rotation causes the singularity to stretch into a ring-like structure. According to the mathematics of Einstein's theory of general relativity, our best current model for understanding black holes, passing through this ring singularity, could theoretically lead to a wormhole, transporting matter to an entirely different region of the universe, possibly ejecting it through a white hole. White holes are hypothetical objects that are essentially the reverse of black holes. They expel matter and light and are theoretically impassable from the outside. Yet, the interiors of rotating black holes present a substantial challenge. The mathematics of general relativity, the same that suggests the possibility of wormholes and white holes, also indicate that the interior of a rotating black hole is extremely unstable. This instability arises from the ring-shaped singularity's rapid rotation, which generates powerful centrifugal forces. In the realm of general relativity, such strong centrifugal forces can act like anti-gravity, repelling instead of attracting. This creates a unique boundary within the black hole known as the inner horizon. Within this region, radiation and matter are drawn inward towards the singularity due to intense gravitational forces. However, as they approach the ring singularity, they encounter the repulsive anti-gravity, with the pivotal turning point being the inner horizon. An observer crossing this inner horizon would be met with a barrage of infinitely energetic radiation, a concentrated blast of the universe's entire past, compressed into a fleeting moment. The presence of an inner horizon hints at the eventual destabilization and destruction of the black hole. However, the observable existence of rotating black holes in our universe suggests that our current mathematical models are incomplete or incorrect, and that there are unknown factors at play. The true nature of what lies within a black hole remains one of the greatest mysteries in modern physics. The unsettling reality is that we may never fully understand the enigmatic heart of these cosmic giants. As you teeter on the precipice of plunging into a black hole, an array of enigmatic questions and possibilities unfurl. What unseen wonders or daunting challenges might you encounter in such a journey? And what extraordinary stories could you recount if you were to somehow defy all odds and return? The cryptic nature of black holes, embedded deeply in cosmic enigmas, renders these questions not just complex, but steeped in layers of scientific and philosophical ponderings. The event horizon of a black hole represents more than a mere boundary. It is the threshold between the known and the unknown. The colossal gravitational pull at this frontier is hypothesized to be so intense that it could dismantle any matter attempting to cross it. This formidable barrier casts significant doubt on the feasibility of survival or return from such an expedition. The genesis of black holes, according to astrophysical theories, lies in the gravitational collapse of massive stars. When a star's core collapses under its own prodigious gravity and surpasses a critical mass threshold, it culminates in the formation of a singularity, an entity of infinite density at the black hole's heart. The gravitational strength of black holes is unparalleled, so much so that not even photons of light can liberate themselves from its grasp. This renders the event horizon an unequivocal point of no return. Theoretical physics provides insights into the extreme and likely destructive physical effects near this point, where the concept of spaghettification, the stretching and tearing apart of objects by differential gravitational forces, becomes a grim reality. The notion of black holes as cosmic gateways to other galaxies or alternate universes has long intrigued scientists and laypeople alike. The idea finds its roots in the concept of wormholes or space-time bridges, proposed in theoretical physics as pathways connecting disparate points in the universe. Yet, the existence of such wormholes, particularly in connection with black holes, remains a topic of vibrant debate and speculation within the scientific community. Some theoretical physicists have ventured further, pondering the tantalizing prospect that black holes could be connected to white holes. Conceptualized as the antithesis of black holes, white holes are theorized to expel light and matter rather than ensnaring them. This concept, though rich in theoretical underpinnings, lacks empirical evidence. If a connection between black holes and white holes exists, it could imply that the process within a black hole might not culminate in obliteration, but could involve a transformation or transference of matter and energy, perhaps releasing them in another form or at another cosmic location. Contrastingly, theories such as the black hole firewall hypothesis present a starkly different picture. This hypothesis posits that the event horizon of a black hole could manifest as a blazing wall of fire, annihilating anything that dares to approach. This fiery demise at the horizon presents a significant challenge to the established theories of relativity and quantum mechanics, suggesting a paradoxical clash between the smooth passage predicted by general relativity and the violent disintegration postulated by quantum mechanics. In the quest to reconcile these paradoxes, alternative theories have emerged. Some scientists propose models of black holes featuring temporary horizons that eventually dissipate, releasing trapped matter and energy. This theory entertains the possibility of information preservation within black holes, thereby challenging assumptions about their absolute destructive capabilities. This perspective aligns with certain interpretations of quantum mechanics, which suggest that information is not annihilated, but rather undergoes transformation. The role of black holes in cosmic processes is a subject of intense study in modern astrophysics. This includes exploring their potential relationship with dark matter, the nature of singularities, and the conservation of information across the universe. Theoretical studies probe these vast concepts, delving into phenomena like Hawking radiation, challenges to the no-hair theorem, and the prospect of black holes being sources or repositories of dark matter. Despite significant advances in astrophysical research and technology, the true nature and behavior of black holes, along with the destinations they might lead to, persist as some of the most profound and tantalizing mysteries in the study of the cosmos. These celestial phenomena continue to challenge our understanding of the universe, igniting curiosity and debate about the vast uncharted territories of space and the fundamental laws that govern them. The exploration of these enigmatic entities not only stretches the boundaries of human knowledge, but also sparks the imagination about the endless possibilities that lie in the expansive universe. Venturing into a black hole, often depicted in science fiction as a portal to distant universes or unexplored parts of our own universe, presents a more complex reality. In actuality, the idea of entering a black hole is fraught with danger and uncertainty. Despite this, there remains a sliver of possibility that someone entering a black hole might have a chance of escape, possibly returning to their original universe or arriving at a completely new and exotic destination. This stems from the fact that black holes warp space itself, potentially bringing points usually far apart closer together. A common analogy used to explain this is the folding of a sheet of paper. Drawing a line on a flat paper represents a certain distance. However, if you fold the paper, the endpoints of the line can be brought much closer, even though the line itself remains the same length. This concept links back to Einstein's theory of relativity and the notion of gravity. A black hole is not just an empty void in space. It is a region where a massive amount of matter is compressed into an extremely small area known as a singularity. This singularity is believed to be infinitely small and dense, although there is some scientific debate about this characterization. As one approaches a black hole, the speed required to break free from its gravitational pull, the escape velocity, increases. At a certain point, this escape velocity exceeds the speed of light, which is approximately 186,282 miles per second. For context, Earth's escape velocity is about 25,000 miles per second at its surface. Given that nothing can surpass the speed of light, escaping a black hole seems impossible. However, black holes don't indiscriminately consume everything around them like a cosmic vacuum. Their influence is limited to their event horizon, the point beyond which escape is impossible. The size of this event horizon increases as more matter is absorbed by the black hole. It might be more accurate to visualize a black hole as a sphere that allows matter in but not out. What lies beyond this surface remains one of the greatest mysteries in astrophysics. Most scientists view a black hole as a singularity where all the matter that contributed to its mass gets compressed into an infinitely dense point. If someone were to fall into a black hole, they would likely be elongated by tidal forces and ultimately compressed into the singularity, contributing to the expansion of the black hole's event horizon. Over time, this matter would be released as Hawking radiation. Physicist Stephen Hawking theorized that black holes emit photons, leading to a loss of mass. This occurs because, based on Einstein's renowned equation E equals mc squared, energy and mass are interchangeable. Although black holes will eventually dissipate, this process is extraordinarily lengthy. For example, a black hole with the mass of the Sun would take about 10 to the power of 87 years to transform into gamma rays, compared to the universe's current estimated age of about 14 billion years, or 1.4 times 10 to the power of 9 years. There is ongoing debate regarding the duration of black hole evaporation, especially since Hawking radiation does not conserve any information about the matter initially consumed by the black hole. Nonetheless, being emitted as radiation is still not an ideal outcome. But what about wormholes? Wormholes present a potentially more viable means of escape from a black hole. Gravity's effect on space can be likened to a sumo wrestler indenting a mat with his weight. Any object creates a local gravity well, which gets deeper towards the center of the object. In the case of a planet, this well eventually flattens out. However, black holes defy this norm. The curvature of space near a black hole intensifies indefinitely until reaching the singularity, where it becomes infinite. In this scenario, the well isn't a depression, but a hole that gets increasingly narrow, resembling an endlessly deep dimple. This mystery deepens when considering Einstein's theory of relativity, which breaks down at the singularity of black holes. These singularities are incredibly small, and at such scales, quantum mechanical effects are expected to appear. However, integrating quantum mechanics with gravitational theory to understand singularities remains an unsolved challenge. The complexity increases with the realization that black holes are not stationary. Most celestial bodies rotate, implying that the singularity within a black hole could, under sufficient rotational speed, form a ring rather than a point. Such a ring singularity might act as a gateway to other universes, akin to the concept presented in Stephen Baxter's 1994 science fiction novel, Ring. This implies that a black hole could indeed be a wormhole, a passage through space and time. The allure of this idea lies in the fact that with a point singularity, any path leads to the singularity if you are within the event horizon. However, a ring singularity could theoretically alter this dynamic. The part that compresses matter into nothingness might not necessarily be in your future due to the unique ways a ring singularity would twist space and time. Yet, the concept of a ring singularity serving as a gateway is far from confirmed. The formation process of such singularities is not understood, and attempts to mathematically model a wormhole created by a black hole encounter issues of stability. Theoretical work suggests that such wormholes might only be feasible with exotic matter, which has negative mass, a concept that remains poorly understood. This leads to a fundamental issue. While many scientists entertain the possibility of black holes as wormholes, definitive answers are elusive without a comprehensive theory of quantum gravity. Furthermore, there's no observational evidence of matter emerging from unknown origins, as one would expect if black holes were portals to other universes. Some theories even suggest that black holes could give rise to new universes and subsequent Big Bangs, with our own universe being a product of such a process, though this remains a controversial idea. Another implication of black holes as gateways is the prospect of time travel. Due to the relativity of time, instantaneous travel from one point in the universe to another could also involve traveling through time, potentially arriving at a destination before departure. Stephen Hawking noted the absence of observed time travelers as an argument against the feasibility of time travel in our universe, casting doubt on the utility of black holes as wormhole generators. While it remains a possibility that black holes could serve as gateways, the prevailing scientific consensus suggests that they are likely not. Black holes, often depicted in popular culture as voracious cosmic entities, have sparked widespread fascination and occasional concern, particularly regarding the potential for their creation in high-energy physics experiments like those at the Large Hadron Collider, LHC, at CERN near Geneva. The notion of creating a black hole on Earth, while a subject of speculative discussion, has never been realized. Furthermore, even if such an event were theoretically possible, the implications would likely be less dramatic than often imagined. This is primarily due to the limitations inherent in human-made technology. A black hole produced in a laboratory setting would be expected to have a relatively small mass and consequently a minimal gravitational influence. It would not be capable of consuming significant amounts of matter, thus posing little threat. The pursuit of creating black holes in controlled laboratory environments is not merely a flight of fancy, but an active area of scientific inquiry. Such research endeavors could shed light on some of the most profound questions in physics, particularly those pertaining to the nature of quantum mechanics and gravitational forces. In the cosmos, black holes are typically the end result of the life cycle of massive stars. When such a star exhausts its nuclear fuel, it undergoes a catastrophic collapse, leading to a supernova explosion. The star's core, under the immense force of its own gravity, collapses to a point of extraordinary mass and density, creating a black hole. This process results in a gravitational pull of such magnitude that not even particles traveling at the speed of light can escape, hence the name black hole. These cosmic phenomena are not just theoretical constructs, but are observed and studied throughout the universe. The safety around black holes is a matter of distance. The event horizon, a boundary surrounding a black hole, marks the point of no return. Once an object crosses this boundary, it is irretrievably drawn into the black hole. The size of the event horizon varies with the mass of the black hole. Larger black holes have more extensive event horizons, spanning millions of kilometers, whereas smaller ones have much more limited boundaries. In a hypothetical scenario where a black hole is created in a laboratory, assuming it has a mass of about 0.5 kilogram, its event horizon would be incredibly small, far smaller than a proton, rendering it essentially harmless. The theoretical possibility of creating a black hole in a particle collider like the LHC is rooted in Einstein's special theory of relativity, which establishes a relationship between mass, m, and energy, E, encapsulated in the famous equation E equals mc squared. The LHC accelerates protons to near-light speeds, achieving high energy levels that, in theory, could give rise to a range of exotic particles, potentially including miniature black holes. However, the energy required to create a black hole with a significant event horizon is orders of magnitude greater than what the LHC can produce. Moreover, any black hole that might theoretically be produced in such a collider would be expected to lose energy rapidly and dissipate almost instantaneously. Speculation prior to the LHC's activation in 2008 included the possibility that if spacetime contains additional dimensions, as posited by string theory, black holes could be more readily produced. String theory attempts to reconcile quantum mechanics with gravitational theory and suggests that gravity's apparent weakness in our observable universe might be due to its effects dispersing into these extra dimensions. In such a scenario, the creation of a black hole in a particle collider could become more feasible, potentially offering groundbreaking insights into the fundamental nature of gravity. However, a committee of physicists, after thorough investigation, concluded that the likelihood of creating a black hole at the LHC was minimal. This conclusion was based on the observation that cosmic particles collide with Earth's atmosphere at energies exceeding those produced in the collider, yet no black holes result from these natural high-energy events. This report was updated and reissued in 2008 to address and alleviate public concerns regarding the safety of the LHC experiments. As of the present day, no black holes have been detected at the LHC, aligning with mainstream physics predictions rather than the more exotic possibilities offered by theories like string theory. In a more recent development, researchers have reported the creation of a simulated baby wormhole using a quantum computer. While this achievement garnered significant media attention, it represents a theoretical and mathematical exploration rather than the physical creation of a wormhole. The simulation is seen as a manifestation of unique quantum mechanical properties of matter that mathematically resemble wormholes rather than a direct physical realization of such structures. Looking ahead, advancements in quantum computing technology hold the promise of simulating black holes, enabling physicists to study their behavior in unprecedented detail based on Einstein's equations. Such simulations could provide invaluable insights into the properties and dynamics of black holes, particularly in understanding phenomena like accretion disks. These disks, formed as black holes pull in and shred nearby material, emit intense light and are a key focus of astrophysical research. Studying these processes in a controlled environment, such as a laboratory, could significantly advance our understanding of black hole mechanics and their role in the broader context of the universe. In the early months of 2023, a captivating research study surfaced, sparking considerable interest and excitement both within the cosmological community and among the general populace. A collaborative effort involving scientists from 9 distinct nations has potentially shed light on the perplexing concept of dark energy, a topic that has long baffled experts in cosmology. Their research posits a potential connection between the elusive dark energy and the colossal supermassive black holes. Should their theory prove accurate, it would represent a groundbreaking shift in our comprehension of the cosmos, paralleling the seminal discovery of dark energy over 25 years ago. Nonetheless, it's important to consider that such a claim might be somewhat exaggerated. Let's explore this subject in more detail. The universe began approximately 13.8 billion years ago with the Big Bang, an event that initiated its continuous expansion. Originally, it was believed that the gravitational pull of galaxies and stars would slow this expansion. Contrary to this belief, in the late 1990s, 2 separate research teams discovered that the universe's expansion was not decelerating, but accelerating. The prevailing explanation for this phenomenon is an unidentified form of energy in space, termed dark energy. This mysterious energy, which seems to act as a repulsive force, constitutes about 70% of the universe's total energy. In contrast, all observable matter, including planets, stars, and galaxies, accounts for merely 5%, with dark matter comprising the remaining 25%. The study in question links the elusive dark energy to black holes, particularly supermassive black holes, suggesting that these cosmic entities might play a role in the universe's expansion. Predicted theoretically through Einstein's equations, black holes are formed when massive stars exhaust their nuclear fuel, leading to a collapse. This collapse can result in dense objects like white dwarfs or neutron stars. However, if the star's mass is sufficiently large, it collapses into a singularity, an infinitely dense point where gravity is so intense that nothing, not even light, can escape. Supermassive black holes, believed to reside at the centers of most observed galaxies, grow over time by absorbing nearby matter or merging with other black holes. They form bright accretion disks composed of matter being stretched and torn apart by the black hole's gravity. However, in the absence of nearby matter, their growth should theoretically halt. The researchers focused on dormant galaxies with inactive supermassive black holes, which should not be growing significantly. Surprisingly, they found that these black holes appeared to have increased in mass by 7 to 20 times over 9 billion years, raising questions about the source of this growth. The scientists proposed that this growth could be linked to dark energy, potentially residing within black holes. To test this hypothesis, they examined similar galaxies at various stages of their lifespans, using the constant speed of light to observe galaxies as they were billions of years ago. They estimated the mass of these black holes by analyzing the relationship between a galaxy's bulge and its central black hole. By comparing galaxies formed around the same time and assuming they evolved similarly, they could track the growth of black holes across billions of years. The scientists proposed a model that links black holes to dark energy using a special factor they called K. In this model, a K value of 0 means there's no relationship between black holes and dark energy, while a value of 3 would mean they're perfectly connected. Their findings indicated a K value of 3.11, plus or minus 1.1. This suggests there's a strong likelihood that black holes and dark energy are related, although it's not yet a definitive conclusion. If this connection is confirmed, it could mean that dark energy, a mysterious force in the universe, actually exists inside black holes. This discovery could help solve some complex problems in physics, particularly those related to the very center of black holes, known as singularities, and could also provide new insights into how gravity works at the quantum level. However, skepticism remains. Correlation does not imply causation, and the assumption that all similar galaxies evolve identically is not guaranteed. More data and a theoretical framework explaining the mechanism of this correlation are needed. If proven, this connection could be a groundbreaking step towards unifying gravity with other fundamental forces and understanding quantum gravity. The implications of this research are vast, but caution is warranted until further evidence is gathered. Black holes rank as some of the most formidable entities in the cosmos. Any celestial body, whether it's a star, planet, or asteroid, that ventures too close to a black hole's core singularity is at risk of being ripped apart by its intense gravitational influence. Should an object cross into the black hole's event horizon, it will be engulfed, never to reappear, thereby contributing to the black hole's increasing mass and size. Essentially, there's nothing that can be thrown into a black hole that would cause it any harm. In fact, if another black hole collides with it, they would simply coalesce into a bigger black hole, emitting a small amount of energy as gravitational waves in this merger. Some theories suggest that, in the far future, black holes might become the dominant constituents of the universe. However, there might be a mechanism for their eventual destruction, or evaporation, as it were. Stephen Hawking, in 1974, proposed a mechanism through which a black hole could progressively lose mass. This process, known as Hawking radiation, is rooted in the well-established concept of quantum vacuum fluctuations. Quantum mechanics posits that any point in spacetime is subject to fluctuations among various potential energy states. These fluctuations are the result of the constant creation and annihilation of pairs of virtual particles, each pair consisting of a particle and its antiparticle with opposite charge. Normally, these pairs quickly collide and annihilate each other, maintaining the overall energy balance. However, at the edge of a black hole's event horizon, if positioned correctly, one particle of the pair might escape the black hole's gravitational pull while its counterpart is captured. This captured particle would then annihilate another particle inside the event horizon, effectively reducing the black hole's mass. To an observer from afar, it would appear as though the black hole is emitting the escaped particle. Therefore, unless a black hole is continuously absorbing more matter and energy, it will gradually evaporate, one particle at a time, albeit at an incredibly slow pace. How slow is this process? The field of black hole thermodynamics provides some insight. Just as we perceive energy release from ordinary objects or celestial bodies as heat and measure their temperature accordingly, black hole thermodynamics allows us to assign a temperature to a black hole. This theory suggests that larger black holes have lower temperatures. The biggest black holes in the universe would have temperatures near absolute zero, around 10 to the negative 17th Kelvin. Conversely, a black hole with a mass similar to the asteroid Vesta would be around 200 degrees Celsius, emitting significant energy as Hawking radiation into the colder surrounding space. The smaller the black hole, the more intensely it seems to burn, and thus the faster it will extinguish. But how soon will this happen? It's a process that shouldn't be eagerly awaited. Most black holes accumulate or accrete matter and energy faster than they emit Hawking radiation. For a black hole with a mass equivalent to our Sun that has ceased accreting, it would take 10 to the 67th power years, far longer than the current age of the universe, to completely evaporate. When a black hole dwindles down to about 230 metric tons, it enters its final second of existence. In this last moment, its event horizon shrinks dramatically until it releases all its energy back into the cosmos. Although Hawking radiation has not been directly observed, some scientists speculate that certain gamma-ray bursts in the sky might be the final throes of small, ancient black holes that formed at the beginning of time. In a future almost too distant to conceive, the universe might become a cold, dark void. Yet, if Stephen Hawking's theory holds true, the once fearsome and seemingly indestructible black holes will conclude their existence in a spectacular final outburst.